In this video we're going to see that every regular and second countable space is normal. This is the first theorem in which we combine a countability axiom with a separation axiom to conclude another property of the space, in this case another separation axiom. Before starting, let me remind you that if you want to support the channel, you can do so in different ways. You can either make small donations or become a member on Ko-fi. That way you can get exclusive content like video boards, early access to the boards, and early access to the videos. If, in addition to that content, you want to get some merchandise, then you can join us on Patreon. That way, in addition to all the other things, you will get stickers, t-shirts, mugs, hoodies, and more. But if all you want is the merchandise, then you can just go directly to our store, where you can buy the items individually. So let's start with the video. To prove this theorem, we will use very strongly both our hypotheses. So before starting, make sure that you understand both of them very well. If you don't worry, we have videos about them. So let's start with the proof. We have a space that's regular and second countable. Let's call it X. And let's say that because it's second countable, we will call B the countable basis of our topology T. We want to prove that this space is normal. Remember that normal meant that the space could differentiate between two closed disjoint sets. So let's take A and B, closed subsets of X, closed and disjoint, so A intersection B is the empty set. Let's make a small drawing so that we can see the situation. Because our space is regular, we know that every time we grab an element A in A, because this element is not in B, we will be able to find an open set U, let's call it UA, and another open set disjoint from UA that contains B. We won't be using BA directly, all we will use is that UA will not intersect B. And we can continue doing this for each element in the space. Now, because our space is second countable, that means we have a countable basis, and so we can always find inside each of these open sets a basis element Bn that will contain A and will be contained in UA. And Bn, because UA is disjoint from B, so will be Bn. Now, this doesn't prove that our space is countable, because if we could actually have another element here and Bn would be covering both of them. So all it means is that because it's second countable, we can get a covering of A by open sets by elements in the basis, and this covering will be countable. So because we have this countable covering of elements Bn, we can take the corresponding elements Un, and that will also cover our space. So let's write all those things down. Given A in A, because A intersection B is the empty set, then A is not an element in B, and so we know that there will exist UA in the topology such that UA contains A and UA intersection B is the empty set. I will not worry about these sets BA for now, so let me just delete them. And we said that because we had a countable basis, then there would exist Bn in this basis such that A is an element of Bn and Bn contained in UA. So for each Bn, we can take the corresponding UA, let's call it Un. And so here, let's make another drawing. We will have a covering of A by open sets. So then the family UN is a covering of A. And now we can do the same for each element B in B. We will find this open set that is disjoint from A, and we can take an element in the basis here and then take the corresponding, let's call them Bn, and like this we will now have a covering by open sets of B. But these open sets, they are disjoint from A, but they could actually intersect these sets UN, because the covering UN could be very big. All we know is that it doesn't intersect B. So these sets could actually be something like this, very big and very annoying. Let me delete this one so that I can make it intersect here. And so these are all the sets Bn. So likewise, let's write this warning down. So I cannot just take the union of all the Bn's and all the union of the UN's and say, okay, those will be two open sets that separate A from B, because they are not disjoint. They have here some intersection. Well, so then the solution to this will be just to remove these intersections. And the way we will do this is, well, let's call it U prime n to the set UN, and we want to remove from this set UN all the possible intersections that it could have with elements in the other covering. So what we will remove is going to be the union up to n of all the B sub i's, so from I equals 1 up to n. But this is not closed, so we need this UN prime to be open. For this to be open, what we will do is remove the closure of these sets. And the same for Bn. Bn prime is going to be Bn minus the union from I equals 1 up to n of the closure of the U sub n. And now, because these two sets are closed, then these two sets are open. Basically what we're doing here is just, well, we keep these that don't intersect anything will remain the same, but when they do intersect Pn, we just remove the closure. But they will still cover A, because Pn are all disjoint from A, and so will their closures because A is closed. So you have something like this. And again, here I have an intersection, so I will remove it. So these vectors are the UN prime, and we do the same for the Bn's. So now the new families UN prime and Bn prime are still a covering of A and B. And now that we have these two disjoint coverings of A and B, we can take the union. Well, obviously, because we should say that there were coverings, A is contained in U, B is contained in B, and U intersection B is the empty set. This is obvious because we were just actually removing in here everything that they had in common. So, because we were able to separate A and B with two open sets that are disjoint, then we have that X is normal. And this finishes the proof.